Here we have the autonomous differential equation, y prime equals y plus 1 squared times y minus 6. The equilibrium solutions are going to be at y equals -1 and y equals positive 6. I've already drawn out the direction field for it as best I could. So first, by looking at it, we have 6 is going to be one of the equilibrium solutions, and it looks like it's unstable based on how the trajectories above 6 are behaving. It's also repelling trajectories below it. So here, let me see if I can write like that. And then it looks like -1 is attracting trajectories above it, but it's also repelling trajectories below it. So that would mean that this one's actually semi-stable. So here we go. So this one is unstable, and this one was semi-stable, also called half-stable sometimes. And then to emphasize which kind of stability it is, so right, this one we usually draw a circle that's open for unstable. In this one we draw a circle, and then the stable side is the top, so we're going to fill that in. That'll show up in the graph below. Alright, well, let's see how that shows up inside f of y. So right, we have y prime equals f of y, and we're going to try using the derivatives first to see what we can glean. So first off, I have my function here f of y, and apparently when you multiply that out, it's going to be y cubed minus 4y squared minus 11y minus 6. All right, and then if you calculate partial f partial y, that's going to be 3y squared minus 8y minus 11. All right, and then to figure out the stability of different equilibrium points, we are going to evaluate partial f partial y at y equals 6 for the first one to figure out the stability there. Apparently when you plug that in, it's 49. Since that is greater than 0, that means it's unstable, which agrees with what the direction field showed us. And then we have partial f partial y evaluated at y equal to -1, the other equilibrium point. That ends up being 0, so it's inconclusive. We don't know if it's stable, unstable, semi-stable based on just this test. So inconclusive. So of course we're going to go and look at the plot of the phase line. And if we plot f of y versus y, it looks something like this. There we go. And so from here you can also see the stability of the different points. So at this point, right, if we have positive y prime on the right of the equilibrium point here, and so the arrows, y is going to increase because y prime is positive, and will get bigger and bigger. On the other side, y prime is negative, right, so that's going to go away. Then they should peak somewhere in the middle there, but then they're going to get smaller and smaller as they get closer to the other equilibrium point. And then this one here, we have y prime is negative again on the other side of this equilibrium point, so it's also going to be arrows pointing to the left, right, correct? So y prime is negative, that means the value of y will decrease if it starts over here. And again, if we want to write those, right, that's going to be an open circle, and this one will be a circle with the stability filled in for the right-hand side. Alright, and that's all the different ways you can try and figure out the stability of the equilibrium points for this autonomous differential equation.